Imagine standing in the Nevada desert in 1957. The Cold War is tightening like a fist. The sky above is wide, blue, and silent. Then someone tells you this: America is about to build a spaceship the size of a skyscraper, powered not by rockets, not by chemical fuel, but by nuclear explosions. Not one explosion, not 10, thousands. And the wildest part? It might have actually worked. The moment everything changed. In the late 1950s, the United States was locked in a silent race with the Soviet Union. After Sputnik 1 shocked the world, space stopped being science fiction and became a battlefield. Washington wasn't just worried about prestige, it was worried about survival. Missiles, satellites, nuclear warheads. Whoever controlled space would control the future. At places like Los Alamos National Laboratory, physicists were already thinking far beyond Earth orbit. Some of them were veterans of the Manhattan Project. They had unlocked the atom once before. Now they were asking a question that sounded insane. What if we used nuclear bombs to push a spacecraft? That idea became Project Orion. The man with the unthinkable idea. At the center of it all was a brilliant and controversial physicist named Freeman Dyson. Dyson wasn't a bomb builder in the traditional sense. He was a mathematician, a thinker, someone who saw patterns where others saw chaos. When he joined the Orion team, the concept was already taking shape under physicist Theodore Taylor. Taylor had worked on nuclear weapons, but instead of asking how to make them deadlier, he started wondering how to use their energy for exploration. Here was the idea. You build a massive spacecraft. At the back of it, you attach a gigantic steel pusher plate. Then, behind that plate, you eject small nuclear charges. Each one detonates at a precise distance. The explosion creates a shock wave. The shock wave slams into the pusher plate. The plate absorbs the blast through enormous shock absorbers. Boom! The ship moves forward. Then another bomb. Boom! More acceleration. Instead of one continuous burn like a rocket, Orion would ride a series of controlled nuclear explosions into space. It sounds reckless, it sounds apocalyptic, but the math said it could work. Why chemical rockets weren't enough. Traditional rockets, like the ones later used in the Apollo program, rely on chemical combustion. They burn fuel and oxidizer to produce thrust. But chemical reactions have limits. The energy density is relatively small compared to nuclear reactions. A nuclear detonation releases millions of times more energy per unit mass than chemical fuel. That means one thing: speed. An Orion spacecraft wouldn't just crawl into orbit, it could accelerate to incredible velocities. Theoretical design suggested it could reach Mars in weeks instead of months, Saturn possibly within a year. Some versions even imagined interstellar probes, missions to nearby stars. And not tiny robotic probes, we're talking about ships weighing thousands of tons, floating cities in space, crewed by hundreds of people. Imagine an American starship the size of an aircraft carrier heading for Jupiter. That was the dream. Testing the impossible. Now here's where it gets almost unbelievable. They tested it. Not with nuclear bombs at first, but with conventional explosives. In 1959, the Orion team built small-scale models. They attached a metal plate and detonated charges beneath it. The models jumped into the air, again and again. Each time the pusher plates survived. Shock absorbers dampened the force exactly as predicted. The physics checked out. The calculations weren't fantasy. Engineers began drafting serious blueprints. Some designs showed a ship taller than the Statue of Liberty. Some others envisioned a 10,000-ton behemoth capable of carrying habitats, laboratories, and long-term life support systems. For a brief moment in history, the United States seriously considered building a nuclear-powered starship. The cost of genius. But there was a problem. Actually, there were two. The first was fallout. Launching Orion from Earth would mean detonating nuclear devices in the atmosphere. Even if each device was small by military standards, thousands of explosions would release radioactive material. In the 1950s, nuclear testing was common. The Nevada desert and Pacific atolls had already seen massive detonations, but public opinion was shifting. Scientists began raising alarms about radiation, cancer rates, and environmental damage. The second problem was politics. In 1963, the United States and the Soviet Union signed the Partial Test Ban Treaty. This agreement banned nuclear explosions in the atmosphere, underwater, and in outer space. Project Orion depended on detonating nuclear devices in exactly those places. With a single signature, the legal pathway for Orion evaporated. The world chose a different path. In the late 1950s, NASA had its sights on the moon. President John F. Kennedy had made a bold promise: land a man on the moon and return him safely to Earth before the decade was out. The focus shifted to practical, politically acceptable technology: chemical rockets, Saturn V, lunar modules. And it worked. In 1969, the world watched as Neil Armstrong stepped on the lunar surface during Apollo 11. It was one of humanity's greatest achievements, but it was also the moment Orion truly died. Because once we proved we could reach the moon with conventional rockets, there was less appetite for nuclear detonations in space. The dream of riding atomic fire to the outer planets faded into classified archives and dusty reports. What Orion could have been. Here's where it gets haunting. According to some projections, Orion could have delivered astronauts to Mars in a matter of weeks. It could have established permanent bases on the moons of Jupiter. It might have enabled missions to the Kuiper Belt decades ago. Some speculative designs even imagined generation ships capable of traveling to nearby stars over centuries. The energy was there. The engineering challenges were enormous, but not impossible. The biggest obstacle wasn't physics. It was fear. And maybe wisdom. Because think about it, thousands of nuclear explosions. Even in space, the optics alone would have been staggering. The risk of accidents, miscalculations, or geopolitical misunderstandings could have been catastrophic. Would other nations see a nuclear-powered spacecraft as exploration or as a weapon? In the Cold War, perception could trigger war. The shadow legacy. Even though Orion was canceled, its influence didn't vanish. The idea of nuclear propulsion never fully died. NASA and other agencies continued studying nuclear thermal rockets and other advanced propulsion concepts. The logic remains the same. If humanity wants to travel beyond Mars efficiently, chemical rockets may not be enough. Today, as private companies push towards Mars colonization and deep space exploration, echoes of Orion are everywhere. When engineers talk about high-thrust, high-efficiency propulsion systems for interplanetary travel, they're revisiting the same fundamental truth the Orion team understood in 1958. To truly explore the solar system, we need more power, a lot more power. The moral question. Project Orion forces us to confront something deeper than engineering. It asks, can tools of destruction become tools of exploration? The same physics that flattened cities could have propelled humanity to the stars. The same atomic fire that defined the Cold War might have ignited a golden age of space travel. There's something profoundly American in that paradox. The audacity, the scale,
the willingness to attempt the impossible. And yet, there's also restraint in the decision not to pursue it. Sometimes progress isn't about what we build, it's about what we choose not to build. A different timeline. Imagine an alternate America. It's 1985. A massive Orion spacecraft launches from a remote ocean platform, detonating nuclear pulses high above the atmosphere. It climbs into orbit, then accelerates towards Mars. Inside are scientists, engineers, families, a floating city on a one-year voyage to establish the first permanent human settlement on another world. By the early 2000s, missions to Saturn are routine. Humanity debates not whether we can reach the stars, but which star to visit first. That timeline never happened. Instead, we remained closer to Earth. Space stations, robotic probes, careful